everyone, today we're going to be talking about proofs for red-black trees. So as a quick recap, let's say we have some tree like this. Now remember, at the end of each of these nodes, there are leaf nodes which are null black children. So I'm not going to draw out the leaf nodes just to avoid clutter, but yeah, at the end of each one of these is a null black child. So the height of this tree, you can find it by either counting the internal nodes, so all the nodes that are not the children, so basically just these three like this, so the height is 3, or you can count the number of edges. So that is also 1, 2, 3. So the height is 3. Now the black height of the tree, on the other hand, is the number of black nodes, as you can probably tell from the name. Now, technically, for black height, you don't count the node, but you do count the null leaf, right? So the technical, most formal definition of black height is you count 1, 2, and 3 at the null right there. But, looking at it visually, you can clearly tell like there's 1, 2, 3. So in any case, black height is 3. Now let's look at this example. What is the smallest possible number of internal nodes in a red-black tree with black height k? And what is the largest possible number? All right, let's look at the smallest first. So in the red-black tree with the smallest number of nodes, the only color the nodes should be is black, right? So let's just take k equals 3. So if k equals 3, what does the tree look like? Well, it's actually something like this, right? And of course, we have all the black null children down here. So let's take a look at the black height of this, right? As mentioned above, right, we don't count the root. We do 1, 2, 3, including the leaf. But visually, you can clearly tell it's just 3, right? Like there's 3 black dots there. So black height is 3, k equals 3, because black height, we're just calling it k in this problem here. All right, let's count the number of internal nodes in this tree, where black height is 3. 1, 2, 3, 4, 5, 6, 7, right? So the number of nodes is 7. Should specify that they are internal nodes. All right, what happens if we increment black height by 1? Let's say black height is 4. Well, the tree in this case would look something like this. And of course, we have the null down here. So if you count all the nodes here, you will find that the number of internal nodes is 15, right? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. So if we continue doing this, we'll see that the pattern is 2k minus 1. So this is the smallest number of internal nodes given a black height of k. What about the largest? Well, for the smallest, it's just, we only have black nodes. But for the largest, we are allowed to incorporate red nodes into this tree, right? Let's, for the sake of space, let's say k equals 2. What is the largest tree we can build off of this? Well, if you think about it this way, right? You just want to expand the tree as much as possible, right? So how you would do that is you would just alternate between black and red nodes for the layers. Now what I mean by that is, right, of course we start off with the black root as always, and its two children are both red. Now we add two black children to each side, and then for each of these guys, their children are all red. And of course, don't forget to add the null black children. So this is k equals 2. And again, this is because, right, formally, legally, technically, we don't count the root, we just count 1 and then 2 for the null child right here. But again, visually, you can clearly tell, right, it's just 1, 2. But technically speaking, you don't count the black root as part of the black height. All right, let's see. Let's count how many internal nodes are in this tree. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. This is 15. And if you keep on doing this, you'll find that the number is 2 to the 2k minus 1. So this is the smallest tree, this is the largest tree. So for this next example, the claim is any node with height h has a black height greater or equal to h over 2, where x is the node. Now the proof of this is if we just think about the properties of red-black trees, right? One property is if the node is red, then both children are black. Because of this property, more than half of the nodes must be black, right? If you just think about it logically, if the node is red, right, both children have to be black. So of course, by this rule, there are a lot more black nodes than red nodes, right? There has to be at least twice the amount of black nodes than there are red nodes. Therefore, this is proven, right? It can be a very simple and short proof like so. The next one is not so short. The next claim is the subtree rooted at any node x contains at least 2 to the bhx minus 1 internal nodes. So with something like this, we'll want to prove this claim using proof by induction. All right, let's see. So the base case is when height of x is equal to 0, right? So x, if the height of x is 0, that means x is a leaf. So any subtree rooted at x just has 0 internal nodes, right? Because remember, 2 to the 0 minus 1, that is just 0, right? So that has 0 internal nodes. Now, going to the inductive step, again, let's suppose the height is this h variable. So the black height will just be bh of x. So any subtree must have a height h minus 1, right? Because think about it like this, right? If you have some tree like this, any subtree you take, it has to have height of h minus 1 because, you know, you're pulling it apart like that. And that is the height, right? H minus 1. And the black height should be either bh of x or bh of x minus 1. Because you can either have the same black height or you can have less than 1 for the black height. So by induction, we're going to assume that each child has at least 2 bh of x minus 1 internal nodes. Right? We're just going to take that and minus 1 because of the property we said above. So the subtree rooted at x will contain at least 2 bh x minus 1 minus 1 plus 2bh minus 1 plus 1 internal nodes. And if we just simplify this, we'll get, if we just do some algebra, we can eventually simplify it down to this. Lastly, we're going to take a look at this lemma. If a red-black tree with an internal node has height h less than or equal to 2 log of n plus 1, how do we prove this, right? So by our two previous claims, n is greater than or equal to 2b minus 1. So remember, this is a previous claim, and then we can just move this to the left. And using log properties, now we can multiply both sides by 2. And now it is proven.